Hey everybody, welcome to the next video. As you can see, I am in lab for this one again. The lights may go off, they may not, I don't even know anymore. Alright, but let's get started here. So in this video we're going to wrap up our discussion of simple harmonic motion. The first thing I want to talk about, though, are damped oscillations, and this is going to just be kind of a conceptual thing. You don't really have to I don't want to say you don't have to understand this, right, but you don't have to worry too much about it. I might ask you like a conceptual question about this on a quiz, but it won't be anything you'll have to actually solve. Any kind of situation you'll have to solve for, because the math gets pretty involved. So what we can do here is we consider, once again, a mass M attached to a spring with spring constant K. And let's say situated on a horizontal surface with one end of the spring attached to the mass and the other to the wall. And this is exactly the same setup that we considered last time, so if you refer to the previous video, there was a diagram of this in there, but it's, you know, it's literally just a mass, say, on the ground, right, with the spring attached to it, the other end attached to it, the wall. Okay, so if we wish to account for damping, we can write the magnitude, or let me say this, we can write that the magnitude of the damping force is given by some constant, and we'll call it gamma, times the speed of the mass, and this will just be v. So actually, let me do this. So we could say Fd is going to be gamma v, and remember that v is actually just x dot, right? The first time derivative of position, like this. Okay, so we once more write out Newton's second law. This time it will obviously be a little bit different, though, because we have a force in this case that wasn't present before. So let's say it looks like this. We still have the hook force, right, because the mass is still attached to a spring, and then we have to account for the damping. And so damping, physically speaking, this could be sort of like air resistance, maybe, or the resistance that an object in a fluid encounters as it moves. Remember, air is a fluid, right? As weird as that sounds to say. So it doesn't have to be a liquid, right? Just a fluid. And this is similar to friction in that it's going to always oppose the motion of the object, and that's why I've written a negative sign in front of this term here, right? Because it should be x dot. Because it will tend to slow the object down, right? And we still have on the right-hand side here, though, that this is the mass times the acceleration, or x double dot. So we just want to put this in standard form. And what that looks like is, well, we just divide everything by, well, let's get everything to one side. I want to write it like this. Plus gamma x plus kx equals 0. Now, this is x double dot still. This is still x dot. And this doesn't change, okay. So let me copy this actually. We just divide everything by m, right? We can do this because this is a homogeneous equation, meaning that one side of it is 0, like that, k over m. Now remember, let me do this one more time. If we want to define a new constant, right, to clean this up a little bit, we could just call this beta maybe, and then this will still be omega squared as before. And I'm just going to say beta is defined to be gamma over m. Okay. Like that. Cool. So then we just have to solve this, right? And solving this isn't as straightforward as solving the case with no damping because of this extra x dot term here. And we're not going to go into the nitty-gritty details of how you would solve this differential equation because this is not a math class, right? But I'll just show you what the solution looks like. So I can do this in Mathematica. Maybe let me zoom in a little bit. So I'm just putting the differential equation in, and I'm using Mathematica's desolve feature, right? This is one of the ways you can solve differential equations using Mathematica. So let's see what it spits out. Sure, that's correct. Cool. Oh right, okay, I have to say that this is equal to something, of course. Let's try that again. There we go. And so this is kind of gross, right? Let me expand this so you can see. This is the solution. It's saying that x of t is given by some constant times this exponential term, right? And then you add to that some other constant times this exponential term. And the nature of this exponential term depends on beta and omega, right? So it depends on the damping coefficient, which is what gamma was. Remember, beta is defined from gamma. And it depends on the spring constant and the mass, in that it depends on omega. And the thing is that there are different cases here, right? So this term up here can be, let's see, it can be potentially imaginary, right? And that's why this gets tricky, because you have to think about the different cases. Essentially, you have to think about how omega compares to beta. And you see that, you know, there's like, I think 3 different cases. There's like under damping, critical damping, and over damping. And so it's like this one problem sort of branches into 3. And that's why we're not really going to do anything more with it. Just kind of wanted to show you what this looks like. The point is that, like, really what you need to know is that I think the easiest case to visualize is where the oscillations die down, right? So you have maybe like an exponential tacked onto a trig function. I can actually show you what this looks like. So a decaying exponential. So let's say I want to visualize this very, very roughly. I'm going to say exponent sine of t. Let's see what this looks like. We'll go t from 0 to, I don't know, let's take it to 0 to 100. And okay, so this isn't doing the best job of showing this. Maybe let me try a smaller time interval. But yeah, so this does okay. It just kind of shows you that it begins to oscillate, it begins to die down, right? And eventually just stop oscillating. And that sort of, I think, makes sense if we if we liken the damping force to, say, friction, which is a dissipative force and takes energy out of our system, right? But that's pretty much all we'll say about this. Okay, but what we want to talk about next is the simple pendulum. So this is going to be a bit different from the mass on a spring, but we're actually going to see that it kind of works out to be the same, and I think that's pretty cool, because these are obviously physically different things, right? Like there's a clear difference between a mass on a string, or I should say maybe like a rigid rod that is very light, and a mass attached to a spring on the ground. So let's dive into this a little bit. So what I want to say is consider a mass m, and we'll say that it can be well approximated as a point mass, and it is fixed to one end of a rigid, lightweight, i.e. negligibly massive rod of length L. And let's say the other end of the rod is attached to the ceiling and is free to pivot. And so this is a simple sketch of what this might look like, right? And so because the rod is free to pivot, right, at the point where it's attached to the ceiling, it can like swing back and forth, and that's very important. It's something very important to note for our discussion here. So, what do we want to do? I think we want to make a sketch of this. Let me bring up the tablet here. So we want to write out Newton's second law for this situation. So say we have the ceiling here, the rod, and then the mass. And let's say at some given instant, the rod makes an angle theta with the vertical. So what are the forces that we have acting on this thing? Well, we're going to have the tension force, and we're going to have the gravitational force. And that's it, right? So let's choose some axes, and in this case I think it makes sense to choose rotated axes. So we're going to say that this line here represents my x-axis, and this line here represents my y-axis. So maybe let me specify that too. Y hat, x hat. Okay, cool. Now we can see, I think, that this angle should also be theta, right? It's a very small theta, but I'm just saying that these angles are the same, right? And so, if we want to think about the torque on this thing, let's see what that looks like. Let's say about the z-axis. Okay, so there's really only one contribution to the torque here, and it's going to come from the component of the gravitational force that is aligned along our choice of negative x, right? And so we could write something like this. We could write, well, remember the rod too is length L, that's important. Let's see, negative mgl sine theta, and then we would write negative I alpha. Now I am just putting the negative signs in here because these, well, because, right, like if we think about our convention for the sign associated with rotation, this torque here, right, would tend to make this thing rotate clockwise, and that would be a negative torque. And because I want to solve for, say, the magnitude of the angular acceleration, I'm putting a negative sign in front of my I alpha term. But if you don't do that, it doesn't really end up making a difference because you just find that your alpha is a negative number, right? So it's totally fine if you don't do that. Okay, so this is the setup here, right? And with that out of the way, I'm going to go back to the document and write this out. So we find for the torque equation that, let's say, sigma tau z equals negative mg L, and we said sine theta, and this equals negative I alpha. And of course we can just get rid of the negative signs. And we can also actually, let's plug in what I is, because remember the rod is negligibly massive, right? So it's massless, essentially. And the mass is always a distance L from our axis of rotation, because our axis of rotation here is like at this point. And so the moment of inertia for this thing is simply mL squared, right? And so this is what our second law becomes. And we could even, clean this up a bit. We can say g sine theta equals, let's see, script L alpha, because we can cancel the masses and we can cancel a factor of L on both sides, right? So this is what we find. And what I'm going to do next is I am going to, let's rewrite alpha equals theta double dot. Because remember, right, that the remember that the linear acceleration, let's say if we're talking about the x direction, the linear acceleration is the second time derivative of x, the position, right? And similarly, the angular acceleration is the second time derivative of the angular position. And this is just in keeping with what we've been doing all along for this rotational stuff, right? Just sort of making analogies between linear motion and angular motion. And so we then find g sine theta, right, equals, and you probably see where this is going, right? This is starting to look like a differential equation, and indeed it is, and that is where this is going. But we need one more thing here. We can't really solve this. Actually, now that I mention it, I'm curious to see what mathematic it gives me if I try to make it solve this. So let's see what happens. We had g times sine theta, and theta is a function of t, equals, is it L times a second time derivative of theta with respect to t, and we have to say, okay, theta t, theta, let's see. Yeah, okay, so we're getting something weird, right? Like Jacobi amplitude, I don't even know what that is, if I'm being honest with you. So this is probably not super useful. And so what we do is, let me say the final step is to make use of the small angle approximation for sine theta, which says, and let's say sine theta is approximately equal to theta. Cool. Now, before we do anything else, I guess I'm going to share a meme with you that I saw the other day. I thought it was pretty funny, and it's very appropriate for this. So Mary Jane is asking Peter Parker to tell her the truth, right? Saying she's ready to hear it. And then he goes on to tell her that physicists approximate just as much as engineers. And she is quite visibly distraught, right? It's disturbing, but it's true. Anyway, so let me say then that with the small angle approximation, our differential equation then becomes, and this is going to be something we can actually solve. Let me just, okay, so it's just g theta equals L theta double dot, right? And then we want to rearrange this, put it in the standard form as well, and we find when we do that, that theta double dot, let me not skip steps here because that's how I make mistakes. I don't like that there's a negative sign there, though. I don't think this is how this is supposed to work. Let me just see something here. Yeah, we're getting an exponential. We should be getting a, let's see, we should be getting a sine cosine deal. Okay, so then I think what I need to do is I need to get rid of this negative sign. Yeah. So I'm going to go through and fix all this. Apologies about that. But we end up just getting the same thing as before, except now one side is still negative, right? Sine of theta being approximately equal to theta, that's still valid. But we end up finding that our differential equation becomes this. Okay. And I will discuss, or I'll address why that turned out to be the case, why we needed to write it like this. But yeah, we'll come back to that in a second. Actually, what I did want to do though is I wanted to just show you something as well. I want to talk about the small angle approximation and just kind of show you where it's more or less valid. So what I'm going to do is I'm going to plot sine of theta, where let's say theta varies from negative pi to pi. And then I'm also going to plot the same plot, just theta, right, where theta also varies from negative pi to pi. Let's see, I think this should be good. Missing a square bracket. There we go. So you can see, right, this straight line here is obviously just, let's say it's f of theta equals theta, right? Whereas this I don't even know what to call it other than a sine function. This is the sine function, right? This is just f of theta equals sine theta. And we see that there's like a region here where these are nearly indistinguishable, right? And it looks like it's from about, say like about negative 0.5 to positive 0.5, right? And that's sort of the regime in which this small angle approximation is good. And that's why they call it the small angle approximation, because it doesn't work for larger angles, right? Like if we tried to say, well, here's pi, right? We can't say sine of pi is approximately equal to pi, because that's very much not true. But in between, let's say, negative 1 radian and positive 1 radian, this is going to work decently well for us. And the smaller the angle is, the better it works, right? So I wanted to bring your attention to that. Now let's come back to this differential equation and talk about why I had to put the negative sign on one side but not on the other. And I would say that the reason for that is that when it comes down to it, that this alpha is a function of time, right? And we need to have that it can assume negative values, right? Because this thing is going to swing back and forth, okay? And you know, in the ideal case, it would just do this forever, right? It's going to swing back and forth, and so it's going to switch its motion from, you know, being say in the clockwise orientation to the counterclockwise orientation, and that suggests to us that this has to allow for the angular velocity to change signs, right? SIGNS. And so that's why this is, and it's okay if this is not clear, it's not a huge deal. I just made a minor mistake. So the reason we had to write it this way without the minus sign is because we need to allow for negative angular accelerations. Because if we think about what's happening here physically, right, we know that this is, as I said, going to swing back and forth, and so its angular velocity will change directions. Okay, that's a little embarrassing, but we're gonna be okay. So what we want to do is we want to put this in the standard form before we move on, and all we're going to do is we're going to divide everything by L. And then we're going to do this thing where we write this as omega one more time. So I'm going to say, well, omega squared theta equals 0. So let me fix this. And let me just make it explicit that in this case now, omega is defined to be the square root of g over L. Cool. Okay, and notice that this is the exact same equation that we came up with for simple harmonic motion involving springs. Now this is, you know, I shouldn't say maybe it's the exact same, because before we had x, right? But now we have theta, but the form is exactly the same, right? It's that some function when differentiated twice with respect to time plus omega squared times the original function equals 0. Now, let me say that one of the solutions to this differential equation is, and we could write this, let's say theta as a function of time equals big theta. Big theta is just a constant, right? I was tempted to call it big A like we did for the one-dimensional simple harmonic oscillator with the spring, but I'm not going to do that because I want to remind you that, well, there's going to be a difference between the constant that we put here and the constant that we had before. But the other part is exactly the same. It's just cosine omega t plus phi, Now, I'm not going to do this, right? I'm not going to differentiate this twice and then plug it into the original equation, but you should do it, right? You should give it a try and make sure that it satisfies it. But maybe you can already see that it will, because when you differentiate this twice, it's going to turn, let's see, it's going to turn into a sine, and then it's going to turn back into a cosine. But it's going to pick up a negative sign, negative SIGN, and also a factor of omega squared, right? So it will satisfy the equation we wrote, but you should check that just to be sure. Okay, and so notice that this looks like, you know, except for the notation, I guess, but this is exactly the same form as the mass on the spring, right? Which is kind of cool, I think. I should tell you now what the significance of this is, and this is, let's say that this, right, so in as much as the, let me write this out, so in as much as the amplitude, right, remember this was A, was defined to be the maximum, and let's just say horizontal distance from the equilibrium position of the spring in the last video, and this big theta, right, this is capital theta, is defined to be the maximum angular position for the simple pendulum. Right, so it's the maximum angle that, if we come back to our picture here, it's the maximum angle that this thing makes with respect to the vertical. And this, I think this makes physical sense, because if you imagine, right, doing this, like grabbing a pendulum and then holding it at rest and letting it go, conservation of energy dictates that it can't, you know, say swing once and then come back to a position that was higher than it started, right? If there are no forces acting on this thing aside from the tension and the gravitational force, that won't happen, right? It will only be able to come back to the same height that it was originally, and that height is determined by the angle that the rod makes with respect to the vertical. And so I think that keeping in mind, right, that cosine of whatever is bounded between -1 and 1, this makes all the sense in the world. And so that's really it, right? This is our equation. And in the process of obtaining this, we found the angular frequency for a simple pendulum. So let's work an example that involves this. So grandfather clock uses a pendulum to measure out the passing of 1 second, right? I don't know if you've ever seen these. Maybe let me try to find a picture. Give me 1 second here. Here's a good one, I think. So like this, right? Like there's this thing that swings back and forth. And this is, you know, this can be modeled as a simple pendulum fairly well, I think. Well, I would say more of a physical pendulum, but still, it is a pendulum. And so let's imagine that, in this case, it's a simple pendulum. So we want to figure out how long the pendulum must be to have a period of 1 second. And we want this, right, because that's the base unit for time is 1 second. So let's see what this looks like. I'll say in the previous video, we found, remember we found that t equals 2 pi over omega, right? Now, we found omega here. It's just the square root of g over L, right? So we can multiply, let's do it like this, 2 pi times the square root. Now, 1 over omega, right, is just the square root of L over g. And so let's put that in. And this tells us that t equals 2 pi times the square root of L over g. So we'll solve this. just make Mathematica do it. And we want to solve this for L. So we find, and I'll put this here, that L must equal gt squared over 4 pi squared. And I actually would like to evaluate this numerically just to make sure we get a sensible result, right? So I'm going to do that. Give me 1 second here. And we find it should be approximately 0.25 meters, right? And so if a meter is approximately 3 feet, then a quarter of a meter is about, what, 0.75 feet? That doesn't sound right, but yeah, I guess if you want to try that yourself, you could just convert it. But this is reasonable, right? We're not getting like an insanely, long length here. And I think that this is all good, right? So there might be more. So, okay, so here's why I'm a little confused by this result, because it seems kind of short, right? But remember that we're modeling the clock as a simple pendulum, which means that we are neglecting the fact that the rod here has mass, and we're treating the mass on the end as a point mass. And so this is maybe not 100% realistic, but to an order of magnitude it certainly is, okay? And we could revise this if we wanted to once we get to this idea of the physical pendulum, which we will do pretty soon here. But I wanted to work another example first involving the simple pendulum. And in this one we have a simple pendulum that is constructed using a point-like mass of m equals 1/10 of a kilogram. If the pendulum is 2/10 of a meter long and released from rest with the rod making an angle of 30 degrees with respect to the vertical, we want to find its angular position as a function of time. So this is just a matter, right, of plugging in, let me say, recall that the solution we found, so the solution to the differential equation, was this. It was theta of t equals big theta times cosine omega t plus phi, right? And so let's just fill this in. I'm going to say from the problem statement, we have theta, big theta equals 30 degrees. Now, we're going to, in general, want to convert degrees to radians when we're working with simple harmonic motion. So I'm going to do that, right? And if 1 radian is 180 degrees, then, no, sorry, if pi radians, right? Okay, pi radians is 180 degrees. Sorry, my mom's calling me. I just saw. I feel bad not answering. Anyway, the point is that this is going to be pi sixths, right? Pi over 6 in radians. So there's that. And the angular frequency will be, we found that was what, omega equals the square root of g over L, right? And so our equation comes, we could write this now, theta of t equals pi over 6 times the cosine of the square root of g over L t plus the phase constant, right? Now, let me just make sure this is all good. Yeah, cool. I think this looks fine. So then all that's really left to do is solve for the phase constant, right? And so let's look at how we would do that. We would say that if at t equals 0, theta of t, or I'll put theta of 0, equals big theta, right? Then we can write this. Theta of 0 equals pi over 6, and remember that this is pi over 6. And we had, I'm going to just copy and paste this actually. And now this is 0, right? This whole term is 0 because we're talking about at time t equals 0. So we simply have that therefore cosine of phi equals 1, right? And so we would see that phi in this case again would be 0. Now I feel like I want to do an example where it's not 0, but I'll probably just give you something on the homework for you to work out where the phase angle isn't, or the phase constant isn't 0. So you can see what that looks like and get a little bit of practice with the idea, because it is definitely not always 0, right? But in this case it is. So I think that's all we wanted to do, right? We wanted to figure out what its angular position was as a function of time. Now I should mention, right, I'm going to come back to this actually, that this equation is important, and what we can do is just differentiate it twice, right? Because this is going to allow us to solve for, let's see, omega of t, right, should equal theta dot. And this should be, I really can't be trusted to try to take derivatives in my head, so just bear with me while I have Mathematica do this. So for the first one, we find negative big theta omega sine omega t plus phi. And then we can also solve for the angular acceleration as a function of time, remembering that this should just be theta double dot. And then we just take a quick derivative one more time, and we find that this works out to be negative big theta omega squared cosine omega t plus phi. So I said I wasn't going to do the derivatives for you, but it just did, so there you go. Because I wanted to make sure that we come up with all the equations for the angular motion here. And now we have them. Okay. So then, okay, let's move on to the physical pendulum. This will be the last thing we talk about here. I meant to have a picture of this, so let me just grab it from the other document here. So I'm going to say first, though, before I put this in, now we consider the more general case of a non-point mass that is fixed to rotate in a plane. Now we could draw it like this, maybe. Like this is just, you know, this is a very general shape, right? This is not like a shape that we have a ready-made moment of inertia for. But we're going to assume that we know the mass of this thing, and we know somehow that we know its moment of inertia. And so we do kind of the same thing, right? Let me bring up the tablet again, and we'll just make a quick sketch of what this should look like, but it will be essentially the same thing here. And I should point out, let's see, I should say that the distance between the pivot and the center of mass for this thing, whatever it is D. And we're also assuming that we know where the center of mass is in this case. So I am going to use the tablet here and do my best to make a sketch of this. So let's see here. It's kind of like that. I don't know, it doesn't really matter. The pivot is here, okay? The center of mass is here. And we know, say that the line that goes from the pivot to the center of mass makes an angle theta with the vertical, and D is the distance from the pivot point to the center of mass. So let me write that in too. I'm going to say pivot, and then this is our center of mass. And the thing is that this looks exactly the same, right? I'm not going to draw the whole thing, but I will draw in the gravitational force again. And the gravitational force points straight down. Remember, that's the point of the center of mass, is that we can imagine that all the mass is concentrated at one location in space. And so we can say that the gravitational force acts at this point. And as before, this is theta, and then we want to just break the gravitational force into its components, right, that are perpendicular and parallel to this line connecting the pivot to the center of mass. And as before, we're just going to find, let me be careful about this time, that negative mg d sine theta equals I alpha. And this again is negative mg d sine theta, which equals I theta double dot. Okay? So with that out of the way, let's figure out what this looks like. So I'm just going to say that our net torque equation gives and negative mgd sine theta equals I theta double dot. So there's that, and we again use the small angle approximation. And so this becomes negative mgd theta equals I theta double dot. And then we want to put this in standard form, right? So we could write I theta plus mgd theta. Now this should be theta double dot. And this is all equal to 0. We're just adding mgd theta to both sides. And then we finally want to divide everything by I, and we'll get that theta double dot plus mgd divided by I theta equals 0. And then one more thing, right? Theta double dot plus omega squared, right? Remember, we're going to define omega to be the square root of mgd over big I is 0. And in this case, omega equals square root mgd over big I, like that. And so again, this is the exact same equation that we had before, right? We just see that the angular frequency is different now. And that's, I mean, that's really it, right? Let me just say this again has solution, and we'll say theta of t equals big theta cosine omega t plus phi, okay, like that. And really the only thing that's different now is our omega, right? And that's sort of been a theme here, is that these equations of motion all kind of break down to the same mathematical form. And it's just that the angular frequency is different depending on the physical setup. And I should just mention that all the formulas and equations that we found in the previous video are still going to work just fine, right? Like we found the relationship between the linear frequency and the period. We found the relationship between the angular frequency and the period. We found how to relate the what was it? Well, for the linear oscillator, we found how to relate the acceleration to the position, right? And all that stuff is going to be the same here, except for in this case, we would want to relate the angular acceleration to the angular position, right? But I don't think that's anything new by this point. That's pretty much how we've sort of approached all things rotational, right? Just by analogies. Okay, so let's look at this example. This will be the last thing we do, and then we'll be done here. So we want to compute the angular frequency and period of a rod of mass m fixed to rotate about one of its endpoints. So it'd probably be a good idea to make a sketch here. So let's do that. We won't really need the sketch, I think, to solve for anything, but we'll just want to maybe have a picture of what this looks like as we go through it. So I'm going to say that this is maybe the ceiling, and we've somehow been able to, like a little hinge here or something, fix a rod to rotate. Now this is not negligibly massive, right? It's going to have a mass that we can't neglect. Theta, and then we'll say that the whole length of the rod is L, and it has mass M. Now, this is what we're thinking about, right? And so what I should say is that we want to consider, let me say, uniform rod of mass M and length L. Okay, so now this is better. This is a better way to phrase this. Okay, so all we need to do then is figure out what, let's see here. We just need to essentially apply this, right? Just fill this in. So let me say we found previously that the angular frequency for a physical pendulum is given by that. And let's see, what's going to change here, right? Well, D, let's look back at the picture here. So the rod is length L, and because it's uniform, its center of mass will be at its geometric center, right? So like there where I drew the little X halfway down the length of the rod. And so we could say, well, D is just L over 2, right? That's it. So we plug that in here, is L over 2, and then we just have to write out the moment of inertia for a rod that is rotating about its endpoint. This is kind of embarrassing, but I'm pretty sure it's the 1/3 ml squared thing, but I just want to check before I do this. I know it's either 1/3 or 1/12. Let's see here. Yeah, it's 1/3. Okay, cool. So we could put 1/3 m L squared for the moment of inertia. And that's it, right? We see that we get some simplification here because the m's will cancel. We have g script L, and then down here we're going to have 2/3 L squared, so we just cancel the masses. We can cancel a factor of L also, right? And then this actually works out to be c square root of g times 3/2 script L, right? Because honestly, I struggle when dividing a fraction by another fraction, so I want to make sure that I do that carefully. But it's just multiplication by the reciprocal, right? And this finally becomes 3g/2L. And so it's almost like we're just scaling the, I mean, it's not like this is what we're doing. This is exactly what we're doing. We're scaling the moment of inertia, not the moment of inertia, sorry, the angular frequency of the simple pendulum by some numerical factor. And that numerical factor in this case is just the square root of 3/2. Okay, and that's it for this video. You'll get some practice with these ideas on the homework, the last homework set, well, the last mandatory homework set. And in the next video, we will move on to waves. And that will be our last topic, so pretty exciting. Cool. I will see you in the next video.